here is the solution, or me working out problem 1 from homework 4. We have this turnbuckle, which we've spelled wrongly. That's one of these things right here. This turnbuckle securing a stanchion on the UHart campus causes a tension in the cable connecting points A and B of 750 newtons. The dimensions are 2 meters between in the x direction between O and B, 1 meter in the z direction of O and B, and 0.5 in the BA right here. So there's 0.5 right there, and then we also have a y dimension YOA, right? So it's the dimension up between the base here and A, which would have been the same thing as the dimension in the y direction between O and D. And we want to find the force vector on the cable that acts on point A. And we also want to find the angles right there. So let's switch over to our paper right here. And while I'm doing this, let me move this over to my other screen so I can read the problem and write out the statement. So right here is page 1, and I am Dr. Deal because I went to doctor school. It's the spring of 2021, and we are in ES110, and this is homework 4. We're knocking them out, and this is problem 1, and I'll make a kind of a sketch of what the problem is. This is good practice because it will help you, to write down and draw the thing out. It helps you to think the thing through while you're taking the time to put these things together. You can start reflecting on how you might approach the problem, what's going on as part of it, right? So it looks something like that. I don't need to make it a beautiful, perfect sketch. Just trying to capture what's taking place right here. Get the axis in there. Boom. Okay, I guess. And we say that we can come down like this right there. Boom, boom, boom. And I know this is like a little bit of a challenging one because of the nature of making it. It's like an isometric drawing, if you recall, or if you even did that. I don't know if there's necessarily know that everyone did, right? So I'll kind of like draw like a little. That's going to be like our little turnbuckle thing right there and there, just to represent it. And this is point C. I don't think we used C, did we? This is point B, and so out of focus. And point A, and there's D, and this was XOB. This was ZOB. This was XBA. I should have meant XAB, right? I like alphabetical order a lot of times, so except that I use the O in there and instead of being alphabetical order totally. But anyway, I digress. And the givens, and I like to put up my time just to see what my pacing is on this, right? So this is 3 minutes in already, and I haven't even finished writing down everything. So you could probably have gone through here, but gone through the zap through this part right here. But I'm trying to give you good practice right here. So this is I'll call that TAB for tension. Focus. Well, not really doing a great job of focusing today. It's because of my plaid. Maybe my plaid is throwing it off. I don't know. Let's see. Other things. We have the XOB is 2 meters. I'll go in the order in which we were given. Oops. I gotta get a new eraser for my pencil. Z, that looks like an OD. Should have been OB. I'll fix it. OB is 1 meter. XBA is 0.5 meters. And YOA is 3.5 meters. And I think that's it, right? And we want to find the force vector on point A, do the cable, that is, and so that's A, and then find B, the direction cosines. The direction angles, I guess. Right. So the first thing we want to do is to establish what this distance is, right? So the best way to do that, I think, is to what we can do as part of this, I don't know if I showed you this way, we could make what was called the position vector. We could have the position of B with respect to A, right? Or I guess maybe in the method that we're doing it right here. Yeah, let's write it out that way. All right, so the position vector of B with respect to A, maybe I ought to pause this and check and see how I did it previously, just to make sure that I'm consistent. Okay, so the method that I have been using right here is to say that we want to find all these little dx's. I didn't necessarily introduce the position vector idea. Make sure we do that in the next class. We'll kind of emphasize on it. Okay, so we have dx divided by d, dy divided by d. Okay, so we want to find this dx, dy, and dz. All right, so that's the approach. I just want to try to be consistent. I know that can be kind of confusing if we mix up the ways that we do things. All right, so instead of, let's see here, boom. Instead of finding the position vector that way, let's take our dx. Okay, our dx is going to be, let's say, x2 minus x1, and our x2 in this case is going to be b, because we're going to go from A to B right there in order to find the force that's on point A, right? So our x direction here, we're going to start off with, if this right here is 2, this distance is 1.5, right? So we're going to go to 2 minus 1.5, right? So what we're left with is 0.5, which is nice, meters. And then dy, we will have, we're going to go from y2 minus y1, which is going to be 0 minus, and then y1 is 3.5, right? So we get a minus 3.5 meters. And then for dz, we take z2 minus z1, and we're going to go from, we're going to end up at 1 meter, and we start off with at 0 meters, right, along this. So 0. So we end up with 1. Okay, and so in the method that we would use in class for this, we would find, I want to take a pause here again. I want to double check. Okay, yeah, so this is, I'm following the right directions. So what I want to do is find the overall distance between these 2 points, and that's going to be just d, and it's the square root of dx squared plus dy squared plus dz squared, right? So the square root of 0.5 squared plus negative 3.5 squared plus 1 squared, and that ends up being 0.5 squared, 3.5 squared, 1 squared, which we don't need to do that. Whoop, I forgot to add this. So 0.5, let me do that again. 0.5 squared, 3.5 squared, 1, and square root. And so it's not much more than the 3.5, because that kind of dominates there. All right, so 3.64. I'm going to double check that. Somehow I'm feeling like I am forgetting to add that. Yes, I did. Okay. I did forget to add that 0.5 squared in there. So it just changed it a little bit. 3.674. Okay. And let's see. I'm going to take the force in the x direction I would find on this is now going to be the total force that we had up there, that TAB right there. It's going to be that 750, and it's going to be times my 0.5 and divided by my 3.674, right? Let me write all these out here. Fy is going to be my 750 times my negative 3.5 divided by my 3.674, and then Fz 750 1 and divided by 3.674. Let me see, I'll square that up with my my page right in there. And plugging those in, 750 0.5 times 3.674 divided, I get 102.1. These are newtons. I get 750 3.5 times, but divided by 3.674, and I get a negative 714.5 newtons. Right, and of course that's the biggest one, and it's going down, pointing downwards. And then 750. I don't have to do that, but did anyway. Dang, don't swear. 0.674 divided. Okay. And then this one is 204.1 newtons. All right. So I can rewrite out my vector at the end, but it's going to have this is I, this is J, and this is K. To answer the other part of it, we have theta x, and we could have actually done this as a step before the other one and then multiplied what those would have been. But we're going to have the inverse cosine of, I guess I'll write out the equation right here so it'll be clear. Inverse cosine of dx over d. So the inverse cosine of 0.5 divided by 3.674, and then the y, theta y, is the inverse cosine. Now you can go ahead and do the negatives in here. That's fine. Negative 3. Well, I meant to be consistent. dy over d. Inverse cosine of negative 3.5 over 3.674, and then z inverse cosine dz over d, inverse cosine of 1 divided by 3.674. So 0.5, 3.674, divide our cosine. I get that it's going to be 82.18 degrees. 3.5, but make it negative 3.674. Divide in there, and then take the inverse cosine. We get 162.3. You have to remember though that that's because it's negative, it's greater than 90 degrees because we're coming around and measuring off of there. I often would probably take the complement of this or in a supplement of this, right? Minus 180, and then 1 divided by 3.674. I'm a little concerned about that 82 degrees right there. I'm going to go back and look at that here in a second, okay? So, I think I made a mistake there. Well, actually, okay, this is 74.21 degrees, right in there. I think that 0.5, yeah, okay. All right, yeah, 674, yeah, I got it, okay. Yeah, divided. Yep, okay, I got it right. So for the answers here, I guess I'm going to write this out as being the force acting on A right there. I think that's the best way to write the thing right there. That's the reason what I want. The thing I want. I'm going to go 102.1 I plus minus 714.5 J plus 204.1 K, and these are newtons, right? So that was the answer A. And for B, I'm going to get theta x is equal to 82.18. I'm going with 4 sig figs. Y is 162.3 degrees, and theta z is going to be 74.21 degrees. And these are we're going to be using this using this a lot when we deal with 3D problems, right? We'll be doing using the position vector soon, so that we can get moments using cross products. But there's the solution. And how did I do with time? It probably took a long time because it took a long time to set the thing up. 16 minutes to do this problem. All right. See you soon.